This video will serve as an introduction to the concepts of electric potential and electric potential energy, which are the two key concepts in Chapter 24 of our textbook. If you take a look at the learning goals of this chapter, according to the AP College Board, you'll notice that there are quite a few elements here. We're going to be looking at the concept of electric potential. You'll see there are lots of things to do there. We'll also be using the principle of superposition to be able to find the electric potential of the ring of charge as well as a uniformly charged disk. We will have to know the fields of certain charge distributions so that you can derive expressions for the electric potential as a function of position. And finally, we'll be thinking about the nature of electric fields in and around conductors so that you can explain why a conductor must be an equipotential. Let's start off with the concept of electric potential energy. We're going to start out with a little thought experiment. We'll say that there are two positively charged particles, Q1 and Q2, that are held in place a distance r apart. Particle 1 is located at point P in the electric field of particle 2. What would happen to that charge, Q1, if the force holding it in place were removed? In other words, if all of a sudden it was free to move under the influence of Q2. Hopefully, you answered that Q1 would accelerate. And if these are two positively charged particles, it would accelerate away from Q2. So not only would it move, but the key here is the fact that it would accelerate. Now, if it's accelerating, really even if it's moving, it would therefore have a specific type of energy that we associate with motion, which we know of being kinetic energy. We also know that energy can't just magically appear. That tells me that this energy had to come from somewhere. Namely, that it had to be transformed from another type of energy. In this case, it must have been transformed from a potential energy. Now remember that we have learned in the past potential energy comes based on an object's position or based on some sort of deformation. In this case, it would be based on a position within an electric field. So we have a special name for that. We call that electric potential energy. An electric potential energy uses the symbol U sub E. A couple other facts here. We know that the electric force is a conservative force, just like the gravitational force. Remember that conservative means that the work that force does is path independent. When we have conservative forces, we can find the work done by that force by finding the negative change in that type of potential energy. A couple other things to point out about electric potential energy here. Often we'll talk about a reference configuration, kind of similar to a reference level with gravitational potential energy. A reference configuration would be a configuration of charges where the electric potential energy of the system is 0. In this case, this would be when all of our charges are infinitely far apart. Also, a reminder that potential energy of any form is always the energy of a system, not of an object. Just like for gravitational potential energy, our system is our mass in the Earth. Our mass, or our object, wouldn't have gravitational potential energy if it weren't on Earth. Here, our system will be multiple point charges or potentially multiple charged objects. We'll apply this concept of electric potential energy to some problems in the future. Before we get there, let's talk about another idea, something called electric potential. An electric potential kind of is a concept that we use to account for this new form of energy. And so we'll say that the electric potential or V, can be expressed as the potential energy of a particle divided by the charge of that particle. It has units of joules per coulomb, since energy is measured in joules and charge is measured in coulombs, which we call a volt. Now, these two terms, electric potential and electric potential energy, they're very similar in name, but they do definitely have different meanings. So I wanted to go through the differences between these two. Electric potential would be the property of a point in space. Specifically, the property of a point in space where the electric field is not zero. Whereas electric potential energy is a property of a charged object in an electric field. So we may say that the point 2, 3 has an electric potential of 3 volts. We would say then that an electron placed at that point has an electric potential energy of a certain value of joules. So notice I say that a point in space has an electric potential, whereas a charge, such as an electron, has an electric potential energy. Additionally, electric potential is independent of the charge at that point. In other words, you can have an electric potential even if there is no charge at the point 2, 3, or whichever point we're looking at. Whereas electric potential energy depends on the charge that's at that point. So an electron would have a different amount of electric potential energy at the point 2, 3 than, let's say, a helium nucleus, for example. Just a couple other quick comments about electric potential. Just like electric potential energy, electric potential is a scalar, which means we don't care much about its direction, but it can be positive or negative depending on the charge that creates the electric field. Additionally, this is how we calculate electric potential, V, be equal to the electric potential energy of a charge divided by its charge. We can also talk about the electric potential difference, which is also sometimes just shortened to potential difference, being the change in electric potential energy between 2 points divided by the charge that has that electric potential energy. Right now, these concepts may seem really abstract, but as we get further on into this chapter and look at some more specifics about the electric potential and the electric potential energy, things will become a little bit more concrete. And we'll see how these things are related to the electric field as we've been studying.